Hello, everyone. Okay, thanks for joining. This is our last tutorial. Okay, so for metal forming. Okay, so let's see the first one. Percentage of cold work is defined as initial cross-sectional minus this. Just use these equations. Very simple. So we said 1 centimeter thick strip of copper is to be cold rolled to 0.7 in 2 stages. We ignore first stage. Anyway, we only calculate the last one, right? Which is 0.7. So determine the cold work percentage. What is the tensile strength and elongation? And what will you do if the thickness is not enough? Okay, so let's see. So quickly review what we have learned. So forming is all about plastic deformation. So that's why we spend so much time explaining all these equations, okay? And this plastic deformation should change the shape of the existing solid metal work. Okay, so it's all about from metal to metal, because last time one student asked about this precision forging. Is it very similar to casting? No, casting is from liquid to solid. Okay, don't confuse them. Casting is from liquid to solid, but forming is from solid to solid. Okay, so these are the fundamental difference. Okay, it looks like similar, right? And we have bulk deformation. We only spent time talking about the forging and the rolling and the sheet, and also we didn't explain it. And also we spent a lot of time explaining what is engineering strain, stress, but actually in metal, we are more often use this, we call it a true strain, okay, true strain and true stress, okay. So this one is a true stress, and also people also call it flow stress. It's the same thing, okay. Different book use different names. Okay, and this N is very important because it indicates the component of strain handling. So strain handling, which means if your strain is higher and higher, so the strains will be higher and higher. Okay, why is so? Because there's a dislocation where every time we talk about plastic deformation, because next year I'm also going to teach 3011 for all of you. It's also called course, you cannot run away. Okay, we again talk a lot about this dislocation generation movement because it's equals to the plastic deformation. Okay, so once you have more and more dislocations, that actually is going to have a lot of interactions, so make the material stronger. And annealing, so how can we get rid of these dislocations? So we can use annealing. Annealing is heat treatment of metal piece after metal forming to lower strains and increase the ductility for further work. Okay, so the purpose of annealing is to lower the strains, increase ductilities. Okay, so according to the temperature, they have different 3 temperature range. So you have either recovery, crystallization, and grain growth. Okay, and also we have, depend on the temperature you're working with, you can either have cold work or hot work. Okay, and besides the strain hardening, we also have a strain rate hardening. Okay, this is a second concept. So once you increase the strain rate, you are going to increase the strength. Okay, so these are the branches of the first part of the of last 2 weeks. Okay, so we said if it's cold work, so normally perform at room temperature or just a little bit above. Okay, in this case, you have whatever you have. Okay, so it's a net shape because there's no shrinkage later, right? So minimal or no machine required. Have a better accuracies, higher tolerance, and the surface is better. And also we said, cold hardening, cold work, you have a strain hardening. That's is good for some time if you need a better strength. And also the grain flow can control, right? You just simply, whenever you want to go, you just push that side. Okay, so grain flow can cause desirable directional properties and isotropic properties, but you need higher force and higher power. So normally you need a bit annealing later. Okay, so that's what we say here. So you can see if you have more cold work, so if cold work is one more, so you are going to have a higher and higher and higher yield strength, which is this blue dot, right? And also you're going to have higher and higher and higher UTS, ultimate tensile strength, but you actually decrease this ductility, right? You can see smaller and smaller and smaller. Okay. because it's narrow. Okay, so this is for the code work, and that's what we can see here. Okay, so determine the total work, and B, what is tensile strength? Okay, very, very simple. Okay, so assume there's no change in the weight of the work metal. Yeah, of course you have to assume, right? Otherwise it cannot move down. So the area is equals to weight times the the height, the thickness h. No, okay, so you can see, so the last one is 0.7 because we only calculate the last one, not the middle 0.8, only the 0.7. So 1 minus 0.7, then you know the percentage of code work, which will be the 30%. It's simply too straightforward. Okay, so then what is the tensile strength here? So I give you the picture already, right? Okay, so since it's 30%, so now you tell me what is tensile strength here? So 30 is roughly here, right? 30 is roughly here. So it's roughly this value. Okay, so since it's 30, so then roughly we know it's about 70 here, right? So in this case, good. Yeah, 70. Thank you, Jonathan. And also if you do this, okay, so then you know the elongation is about 20. Am I correct? So very simple, right? Okay, so for 30% of code work, so the tensile strength is 70 KSI. So don't worry about the unit, you just keep it, okay? Because anytime if you need to do the conversion, check online, it is always available. Very simple. Elongation is about 20%. So that's what we said here. Code work, more code work, you're going to have a higher tensile stress, you're going to have higher hardness, but lower elongations. Okay, so these are very easy to understand. Okay, so what if 0.7 is not enough? I need further reduce. What can you do? Because material is too hard now, as we said, right? If you keep just give them higher, the hardness too much, so you cannot further down, you cannot further do any process. So what can you do? Can you type the keywords here? Jonathan? Gerard? 生之, 于宣, annealing. Excellent, excellent. Okay, so we said annealing. Okay, so heat treatment of metal piece after code work. The purpose of annealing equals to the lower the strength, increase the ductility. Okay, so we said you have 3 stages, 3 events take place. Okay, starting with recovery and recrystallization and green growth. Okay, so you can see again, temperature higher, so you're going to have reduced strength, reduced hardness, but your ductility is increased. Okay, so that is the annealing. Good thing about annealing. Okay, so that's what you can put here. Conduct annealing. Always keywords. You have these words, I give you half marks already. Okay, before subsequent rolling to soften the materials, therefore further rolling become possible. Okay, and the annealing soften materials, degree of softening could be controlled by temperatures. Okay, so if it's higher than this melting temperature, so lead full recrystallization and the softer materials. Okay, so this is the solutions and reasons. Okay, so now we move to the question 2 of metal of a flow curve with parameter K constant, N is constant, and string handling, which is this. So a tensile specimen of this metal with length which is 100 stretched to 157, determine the flow stress at this new length and average flow stress the materials was subject to. Okay, so the first question, actually very simple, right? Very simple. I think that's why I said this 2 weeks, the content is very straightforward. Okay, for most metals at room temperature, strengths increase when deformed due to the string handling, right? String handling. So we can use these equations, K, N here. Okay, so this Y is a flow stress, K is a strength coefficient, so it's a constant. N is also constant, string handling exponent is constant. So actually you only change is this one and this one. Okay, you simply just change these 2. Correct, right? So first of all, for this question, so we know that the initial length is 100. So we stretch to 150. So in this case, you are calculating the flow stress, which is this one. So you simply just need to calculate the true strain. Am I correct? So can you type your answer here? What is the flow stress you have calculated? 舒阳于双来生之 669. Okay, so let me see whether correct or not. Okay, so determine first of all what is the true strain here. So true strain equals to norm L over L naught, so 157, so which will be the 0.451. Okay, so the flow stress, just put 0.451 there. So just use the right calculator, you won't get it wrong. Okay, 669.4. Okay, let me see. Correct. Okay, but with this without this, it doesn't mean anything. Okay, you have to always have the unit. Okay, so this is question 1. Then the second question, what is the average? Average is just divided by 1.3, 1.3, which the final answer which will be 515. Okay, 515. Okay, I'm not particular about the correct answer, like 6 is 9.4, 0.5, 0.2. It doesn't matter at all. You know, for me, if I say roughly that, then because we're engineering students, you don't really need to be so precise with your calculations. Roughly there, then I think it's okay already. Okay. So this is a tensile specimen. Okay, so let's continue. So if I change my flow stress now, the second question. Okay, so if it's subject to a flow stress which is 700 megapascal, what would be the average flow stress? Okay, so I change to the flow stress which is this, which means now I have this value, right? And this is constant. This is also constant. So in this case, what you need to calculate here is actually the true strain, right? Am I correct? True strain. Okay, so let's continue. Okay, so if YF is now changed to 700 megapascal, okay, so then we will have 700 over 800, right? So in this case, we can do a little bit. Okay, K. So we just put it there. KF, okay. Right. So then what you can do is you just put the N1 here times N1. Okay, then this will be 1. So the strain is equals to 700 to 800, 850. So over 0.3. Okay, so this 1 over 0.3, which is the exponent here. Okay, 1 over n. So in this case, the true strain is actually 0.524. 0.524. Yes, you're correct. Karen, there's no need, right? Of course, there's no need. Simply just YF over 1.3. Okay, so what will be the average flow? So we can say is the okay, so it's the same as this. Okay, so which will be the actually just 700 over 1.3 over 1.3. Okay, so we just show everything, all the step here, so it will be easier for you. Okay, so the final answer for once you change to the flow stress to another value, so the average one now changed to 538.5. Okay, because this one is equals to 700. Okay, so maybe the question need to put another one. What is a true strain now? What would be the strain and the average? Okay, so that's question 2. Question 2. Okay, so let's continue. A hot working operation is carried out at various speed. If the coefficient is this, sensitivity is this, so determine the flow stress if the strain rate is this. Okay, so this is the equation. Okay, so we said the flow stress is again not only a function of the string hardening, it is also a function of temperatures, and also it's a function of this string rate. So at hot working temperature, the flow stress depends on the strain rate. So strain rate increase, so deformation is more difficult. So this one we said is a strain rate sensitivity. So use these equations. Okay, we use a new equations, which is here. Okay, so very simple, right? So put the value in here. So 0.01 here. So M is 0.15. C is 210. So what is the answer for the first one? Have you done it? The first one? Okay, Jonathan, thank you. So will be one, yes, correct. You just use a correct calculator. So put the value in here. Put all this value in. Okay, so with 1.5. So the second one, I expect more answer. Can all of you type? When I change to the strain rate to 1, what is the answer now? All of you answer. Any more answer? All of you. Because this is a straightforward one. Okay, so if you just change to 1, right? So this is just 1, then it's just simply 210, 210 megapascal. If I change to 100, okay, so you can see it's nearly more than doubled, roughly doubled. It's so you can see, so the strain rate have a very, very high influence on the strings. Okay, so now I'm asking you, if you want your materials can continue for more processability, so you want the strain rate high or low? Tell me, can you type? If you want your materials have good processability, which means you can, if you roll one, you can roll one more time. So you prefer this strain rate is high or low? High or low? Can you type? Because in most applications like rolling or forging, people need that done a few times. One time is not enough. Just as what we have seen before, right? So at the very beginning to reduce from 1 centimeter to 0.8 centimeter, then continue from 0.8 centimeter to 0.7 centimeter. So it's always a few stages. Yeah, correct. Okay, so that's what we hear. Normally, okay, flow stress increased when the strain rate is increased. This is very common, but normally we prefer a bit low strain rate. Okay, it's because you can just continue with further, if the for example, if you found, hey, the thickness is not correct, right, I need further reduce a little bit, so you can continue to do it. Okay, so normally we still need a bit low strain rate. Okay, but too low strain rate, you also have too much time, so it's also always a balance. But in general, in order for good processability, we prefer low strain rate. Okay, so that's number 3, question number 3. So now we move to the 4. This is rolling. Copper strip have 228. Width is this. Starting one, thickness is this, and with this. Okay, the radius is this. Is RPM. RPM. Okay, so I said RPM is different now. RPM. So average flow is this. Okay, calculate all the roll force and power. Okay, so this is rolling. So we said rolling, take one point. Rolling is a workpiece is reduced by compressive force, and this force is coming from 2 opposing rolls. I said 2 opposing rolls. Okay, it's not only one. One cannot move forward, right? You need 2. Okay, and also there's some definitions such as forward slip, draft, maximum draft, and reductions. Okay, and also we have mean flow stress, and also calculate the mean flow stress and roll force, torque, and power. Okay, so all these things we can calculate. And also we have hot rolling and cold rolling. So in both cases, you always need to do a little bit what we call a pre-treatment. So some people call it a surface conditioning. Okay, so for example, use torch to do this scuffing. So scuffing is remove the scale, because a lot of metal, they have a layer of oxide. So you have to remove all this oxide, or simply just grinding. Okay, so hot rolling normally carry out at a bit above this recrystallization temperature. So in this case, right, so no matter what, if you have some defects, your starting materials have very big grains or very brittle or porous, which means have a lot of defects. So you can, after your recrystallization, you'll become much finer and more uniform, because this one will give you the increased strength and hardness. Okay, so this is a hot rolling. And also the cold rolling, okay, you also need to the surface condition, use exit, sorry, and the basting with water or grinding. Okay, so in this case, we carry out a room temperature, better surface finish, but you may have anisotropic properties, because the cold rolling, you're going to give a preferred orientation of the grains, right? Okay, then we have these 4 different type of the defects of this rolling. Okay, so draft defined as this minus this. Okay, and the reduction defined as D over H naught. Okay, and also we have an important concept here, because you can see why this whole thing can move forward, because you give them a very large this friction force in between, right? So you need a sufficient friction force required to pull the workpiece between the rollers. So the maximum draft is dependent on this coefficient and the roller radius. Okay, so the principle is when your D is less or larger than D max, so we set this friction force is enough. So what is the condition for the friction force is enough? Tell me. So it's less or higher? Yes, very good. Okay, so only when your D is less than D maximum, so which means you have enough frictional forces. Okay, so then your workpiece can move forward. Okay, so D is less than D maximum, suggests that this is enough for this roll to move and also squeeze the workpiece forward. Okay, so this is a condition. Okay, so let's continue. Okay, so the force equals to L. L is this one. It's just this contacting area between contacting length between the roller and workpiece. So we simply use this equation, square root R radius times is D draft. Okay, then the force equals to L times width times this average true stress. Okay, so let's continue. Okay, so and also we set flow stress equals to force over area. So you can use a width times L, which is contacting between the roller and the workpiece, right? So this is approximation average one. Okay, so this is one way. So and also torque. Torque basically what we assume is we assume this force act in the middle of this contacting arc. Okay, so in the end, you just need time half of the length, right? Okay, so that's torque. So continue. So we have power. Power equals to torque times angular velocity. So since we said, if you just rotate 1 round, which is going to be 2 pi, but in 1 second, you can rotate this n number of rounds. So you have to times n, right? So that is angular velocity omega, and tau and this torch we have defined it before 0.5 FL, and if we times these two together, so we get P equals to pi MFL. Okay, but bear in mind this one only applies to 1 row. Okay, 1 row. Okay, but we said before, in order for the whole system to move, for the workpiece to move, you need 2 rows work together, right? 2 rows work together. Okay, so that's why the overall power you need times 2. Overall power you need times 2. Okay, and also in this case, the M, right, is a rotational speed per second, but in reality, people always use per minutes, RPM, right? This is more often. So that's why if we change this n to m prime n prime, it is equals to per minute, okay? So we have to divide it by the 60 here, okay? So that's why you can see you have a 2 here. The 2 is coming from the 2 row, 60 is coming from the minutes, okay? Because you have to convert back to the second, because the watts is in second, okay? So let's continue. So in the end, in most cases, we simply use these equations. Okay, so let's continue. So first of all, the force, So obviously you need to calculate the L, right? So L equals to RD. So we put square root. R is 300, right? Draft is 5, okay? So the answer for this one is 78.7. So the force, so what's your force here? Can you type your answer? Can you type your answer? Some of you are so quiet. Jerry? Jaden, also Jaden. Jaden, I insist you answer this question. Have you done it? Yu Shuan also. Sen Zhi. Jonathan, I think a little bit, man. A little bit. Let me see. Okay. So let's continue. Okay. So this one is give to you already, right? Flow stress is 180. So this will be the 38.7 and 228. Okay. Oh, it's 1.59. Yeah. 1 point. Jaden, thank you so much. Wow. Okay, I insist that you answer correctly. Very good, Jaden. Well done. 1.59. Yeah, you also, I'm very happy that you put the correct unit. Excellent. I think Jonathan also okay, because Jonathan, you put KN, right? Excellent also. KN also okay, because you put 1000 KN, then correct also, because the final answer will be mega N. Okay, so why is so? Because we have to get rid, everything have to change to meter, will be easier. So we always use Newton, meter, Pascal. All these are standard units, okay, SI units, okay? So in this case, since it's a millimeter, so get rid of this millimeter, become divided by 1000. This one also divided by 1000. Okay, so then this mega will be here, still here. All these things you just times together will be 1.59 mega. And also we know that Pascal, okay, and equals to N over square meter, right? So you have meter, you just cancel each other out. So the final answer will be 1.59 mega Newton. Excellent. Okay, Jaden, well done. And also Jonathan, correct. Clarence, let me you have to have 6, 1, 1, 2. Yeah, you're also correct, I think. Right? Correct. That's very good. Okay, but just make sure you have the correct units. Okay, so this is force. So let's continue. So the power. So power, since I give you here is RPM, minutes. Okay, so let's continue. So 2 pi, use these equations. I put the 2 pi. Okay, RPM, N is 100 RPM. And this one we just calculate is 1.59 mega Newton, and L is 38.7 millimeter over 60. Okay, again, we don't like this millimeter, right? Get rid of 1, divided by 1000. So all the rest you don't really need change. Okay, because this one can get rid of already, because we divide it by 60. Would become second already. Okay, so let's continue. So in this case, oh, I give you answer already. So can you type your answer here? What's your answer here? What's your answer here? Jerry? Okay, correct. Okay, so remember here, it is this kW is 1000 watts. Okay, so just be careful with the unit here. Okay, 645 kW, kilowatts. Okay, so that's question 4. Okay, so the last question, what are the advantages of forging compared with machining? Name 3 types of forging method and analyze the flash. Okay, so take on point for the last part. Forging is a work compressed between 2 dies, either by compressive or impact. So we have hot or cold, impact or press, right? We also have open die. Open die is metal to flow laterally with minimum constraint. And you're going to have barrel effect if you have very high friction between the die and also the workpiece. And this barrel effect is very pronounced in hot forging. Okay. And impression die forging, we also call it closed die forging. Okay, so the die contain cavity or impression that imparted to the workpiece. So in this case, you're going to form a flash. And we said flash, the function of flash is stopper. And the freshness is a precision forging. So workpiece is completely constrained to the die. Okay, so no excess flash is created. Okay, so that's a precision one. And the good thing for forging is I can change the grain orientation, but machining does not. Okay, so that's the take-home point. So first of all, what are the advantages of forging? 4, higher production rate, right? You don't really waste anything, right? Waste very little. So for example, if it's a flash, when you waste the flash, okay, but in many, especially for precision, you finish almost nothing. Okay, so less waste of metal, and also because machining does not change the strings, am I correct? Okay, but forging, you're going to have either the string handling or string rate handling. So all this is going to give you a bit higher strings. Okay, so there's a greater strength. Okay, and also the other thing is because the metal are in the forging, you're going to have change. You can change your grain orientation. So this is very, very important. Okay, so we have favorable grain orientations. For example, so if you start with a workpiece like this, so this is a grain direction. Okay, so now I'm asking you, which one is forging? A or B? Can you type? Which one is forging? Okay, Jonathan, B, Clarence, B, Jaden. Jaden left already. Jaden, are you still here? Senju. Okay, maybe he catch the last part already. Okay, Jarrell. Okay, anyway, doesn't matter. Yeah, obviously. So this one is forging, right? So you can see the forging, so the grain can flow with the forging. Okay, so this is very much preferred. Okay, so if something like this, like all this point, is going to be we call it a stress concentrator because you book the grain here, so it's a stress concentrator here. Okay, so this one requires a favorable grain orientation in the metals. Okay, so these are the advantages. And name the type of forging method. So just have to review open, close, and precision. Open one is compressed between the 2 dies. So for example, so you only have this constraint coming from the interface here, right? This is only constraint. Okay, constraint. So for example, if no friction, so now I'm asking you, so you have either some shape like this, because in the end, so the thickness will be reduced, diameter will be bigger, or you have something like this. So which one have friction? So which one, A or B? Which one have very large friction between the interface of the die and the workpiece? Which one? A or B? A or B? Jonathan? If you have very high friction in between the die here and the workpiece, yes, B, B, okay? So since you have very large friction, which means you cannot move here, right? So which means this portion is going to get constrained, okay? But this direction, they can are free to move, okay? So that's why we call this is biennial effects, okay? Something like this, biennial effects, okay? Because the middle one can move, but interface cannot move if you have very high friction, okay? So this is open die forging, okay? Impression, okay? Impression, so you have cavity here, so this cavity here, okay? So normally have a bit higher temperature, so you can have lower force and the ductility is higher, okay? But the issue for this, it's not an issue, okay, but for some applications, maybe an issue because they're going to create this flash. Okay, this flash, which means it's useless later. You have to get rid of it. So some of the material flow out to form flash, so you can get rid of. Okay, so, and also the freshness forging to solve this issue, because you're going to weight some materials here, right? So we have this precision. So everything is constrained by the die. Okay, so no excess flash is created. So that's the three things. Okay, the thing is precision forging, you need a special and a more complex equipment. For example, something like this. And you also need precise control of the black volume and shape, and also accurate positioning of the black in the dilatase. And also normally applies more for this softer, I know it's softer things like aluminum and magnesium. Normally they have better ductility, so it's easier to deform. Okay, so instead of like a flash, you always have something extra here. Okay, so name the three types. Okay, so we put open die is compressed between the two flat dies, allow the metal to flow laterally with minimum constraint. So closed die contains cavity and impression that imparted to the workpiece. So metal flow is constrained because the flash is created. Flash is more or less like a stopper. And the freshness forging, so workpiece is completely constrained in the die, so no flash. And it's critical to have workpiece volume to exactly match the volume of the product. Okay, so that's why we call it precision forging. Okay, so that is the three type, and also the flash. The flash. Okay, so we said you have flash, right? So but flash is actually good. Okay, the flash is formed by the metal when it's flow beyond the die cavities into the small gap. Okay, so which means you can say a little bit materials can squeeze out here. Okay, so that's what we put here. Okay, so beyond the gap, cavities into the small gap, so later have to be trained. So the high pressure give high frictional resistance in the flash. So which means once this one formed here and also closed, so you have very, very high friction here. So you have too high friction here, which means the metals will be more difficult to continue to squeeze out. So make this flash as a stopper. Okay. That's what we say here. So actually, if you use this answer, it's good enough already. Okay. Maybe add up with this. Okay. So flash is formed by the metal that flow beyond the die cavity into the small gap between the die plates, and the high pressure give high frictional resistance in the flash. So then it will prevent further radical outward flow of the materials in the die. Okay, so that's what we said, the function of the flash. If you use just simply one word, it's just a stopper, stopper. Okay, so then materials can flow to least resistance, simply just go into the die cavities. Okay, so this will be more significant in the hot forging. Why is so? Because if the hot forging, right, so the farthest, the cooling place is still here. So this will be the farthest cooling place. Okay, so which means it become more solidified and become more resistance. Okay, even more significant. So compare with the things inside the materials, inside here. Okay, inside here. Okay, so that is the whole answer. It's a video, it's not radical, video. Yeah, video, which means this direction. Okay, so that is the answer for this question. Okay, because Prof after talk passed down this answer, but personally I think too much. You can read through. The flash is formed in the impression for die forging. It is outlet for the slight excess metal in the workpiece. And maybe later I give you two answers. Okay, I myself prefer this answer. Okay, it doesn't matter which one you use. Okay, the flash is formed in the impression die forging. It is outlet for the slight excess metal in the workpiece, and as it's difficult to get the exact volume. Yeah, correct. As flash cools faster than the bulk of the workpiece, it will be stronger and prevent the hot metal from continuing to escape through the gap. So there will be a very high friction between the flash and the die. So this is also going to prevent the flow of the flash once it forms. So the fresh more is like a seal the gap. So more is like stopper, force the hot metal to fill the dead cavities. So this is answer passed down from Prof. Afitor, who used to teach this one before me. So I teach this one for the first time anyway. So yeah, this answer also okay from what we have seen in the lecture notes. Okay, so that is all for today. Any more question here? So let me stop the recording first. So anyway, see you this Friday, 4:50 for the math tutorial, okay?